Okay, so if we're talking about structural members, we want to talk about beam deflection some. Alright, so we need to understand the modulus of elasticity, and that's the ratio of the stress to the strain in an object. And we haven't talked about stress and strain yet, but we will, so I just want you to be aware of that definition. And it's really the stiffness of an object, okay, and it's a chemical property, so it's going to vary from material to material. Wood will be different than concrete, than ABS plastic, than steel. Okay, so all the different materials will have different moduluses of elasticity. Alright, a high modulus of elasticity, in general we say, produces a greater resistance to deformation. However, once things with high modulus of elasticities deform, they're not going to snap back either. Alright, so let's look at two different beams. We have a beam A that's made out of Douglas fir, and we have beam B that's made out of ABS plastic. They both have the same length between the span, they both have the same width and height, and so they both have the same cross-sectional area and the area moment of inertia. The difference between these two beams is the material of construction. Okay, so that material of construction directly affects the modulus of elasticity. Alright, so with different moduluses of elasticity, if we put the same load and put them in the same situation, which one is going to deform more? Alright, so you can see here that it is the plastic beam that is deforming more based on the load. You see how that beam is bending a great deal more. Okay, so why did it deform more? It's the difference in the modulus of elasticity, okay, and that's the ability of a material to deform and return to its original shape. So some things that affect how much something is going to deflect are the applied load, the span between the supports, the modulus of elasticity, and the moment of inertia. Okay, everything was identical on these two beams except the modulus of elasticity. So when we look at the calculations for this, it's the same formula. You saw that previously in this module. Alright, but look at the difference in the modulus of elasticity. Alright, this was an 8-foot length, 1,800,000 psi for Douglas fir, and less than 500,000 for ABS plastic. So if we calculate the beam deflection for the wooden beam, okay, we substitute in all our values for the maximum deflection. Please note that the length was changed to inches. We have to keep the units consistent or our answer won't work out correctly. We end up getting a maximum deflection of 0.123 inches. It's a very small deflection. Okay, now we're going to plug the same numbers in for the ABS plastic beam, except the modulus of elasticity is different now. So again, plug in all my numbers to my formula, my force, my length between the span, my modulus of elasticity, and my area moment of inertia. Okay, crunch the numbers, and I get a deflection of 0.53 inches. Alright, so the comparison between the Douglas fir and the ABS plastic is 0.123 inches to 0.53 inches. That's an enormous difference. Alright, so we get greater than 4 times the deflection in the plastic beam.